We're recording.
All right, and we're back online. Did you guys see the Hunger Games?
I did. Yeah.
That just reminds me of the whole broadcast. Oh man, see, Brad, this is what you get to hear about. I hated the third book, like with a passion.
We're saying it's fine.
Have you read the books?
No.
Oh.
I read the first two.
Let's just start up to the movie was better than the book.
Let's tell me.
I thought it was going to be because the second movie fixed all the problems in the book, and there are so many. But the third movie just reminded me of how bad this author is.
Yeah.
So bad. Sorry. Lots of people I've talked to, I hated it. But
it was painful to watch.
But other people have really liked it. A lot of people have really liked it.
I liked it, but mainly because I didn't read the book.
The reason it reminded me of this is because, and you made this would happen to me, let a woman control. From my point of view, it is a flaky woman's point of view of what warfare is about. And it's all about commercials and costumes and propaganda and God forbid we have any actual tactical thoughts on anything. No, but we have to worry about the outfits and the speeches and the infomercials. That's what war is about. It's terrible.
And shooting.
And shooting arrows that take down giant.
That's what I was gonna say, but I didn't want to spoil it for them.
Well.
That's like with the death. That's like.
Might as well not even go see it out there.
It's like taking a BB gun to a tank.
She shoots arrows. That's not a surprise.
No, it's like shooting the magic patch in the Death Star.
Okay.
I was gonna say BB gun to a tank. Well,
No, the Death Star. It's like when you shot the thing through it.
All right. Admittedly, that was my fault, but we have to go on.
no, we don't. Let's talk about how much you hate it.
A lot. Okay, back to this. Now, there's an important thing here. So now we have some sort of solution, but the solution is incomplete. We need boundary conditions. Boundary conditions always confused me as a student, so I'm going to try and clarify. The idea of boundary conditions, all it means is that we have something in here, but it's incomplete. It has to jive with what's going on out here. What's jiving out here is 0. The particle cannot be there. Okay? So what this means is that we have this idea of the smoothness. Remember we talked about that before? So we can't have the probability end just here. We can't say, no, I'm just going to end right here and then but have 0 out here. If we try to take the differential here, that's going to be bad news. We need something that's going to be smooth. I don't care what the heck happens in here, as long as it's smooth on this side. And, in fact, it needs to be smooth on this side coming out as well. So that's important. And we talked about that before, having the derivatives on the side being infinite is kind of bad news. Now we're lucky on this because if we define this box as being 0 and L right here, on this side we have the sign of x being 0. That already does equal 0 for x equals 0. Done. We don't have to worry about anything. It's nice and easy. Now the next part though is not so easy. I need for psi of x equaling a sine of KL to equal 0 as well. Okay, so that's slightly more complicated. Makes it a little bit difficult. Okay, so what are our options in this? Well, if we need this to equal 0, our first option is to make a 0. We can just make a 0. Well, that's meaningless. That means that a would be 0 everywhere, and the whole probability function. What? It means no energy? Yeah, it means no energy, no probability. I mean, the whole point here, we're going to get a little bit, is that we have to integrate this and we have to get back to 1 for the normalization function. In other words, when you look for the particle, you have to find the particle. If we set a to equal 0, that means the particle doesn't exist. So that its probability is 0 everywhere of existing. So that's a problem. So now if we set what?
So now if you don't let it be.
So that sounds a lot of problems.
So a cannot equal 0. L cannot equal 0. You know, I was giving a talk to some professors before. I said one of the problems we have sometimes with students, depending on their level of interest in the course, they will accept anything you say. Just they don't care. Just tell me what I need to know that I can put it back on the test. Yeah, well, see, but classes are better when you trust nothing and are asking questions and are actually trying to mentally figure stuff out. And I said, what? And we got into the discussion. I said, well, it also depends how close are we to December, because if we're close, then no, nobody's in that book. Just give me the numbers, give me the facts, give me the hell out of here. I want to break.
But you see, you also hit that point though where you get high enough physics that you just start assuming everything you know is wrong.
Yeah, I guess that I could see that.
Or that's when an algebra-based student comes into this class and needs to know like everything. just need calc-based physics and calculus 3 and...
I was thinking about this earlier. I forget how you got shoved into here. You're an education major?
What?
Why do you have to, why do you need to
It's an insult.
No, but why did you have to take modern?
For optometry, regular physics needs like some modern in it, since you guys don't have it in regular.
I couldn't remember why you had to.
Education.
Isn't Brad in education?
Yeah.
Well, this school, the only other requirements for this course are, if you're not physics, it's education. I forgot you were in your own special class because of grad school requirements.
Yeah. At least for Ohio State, we need modern. So.
Gotcha. Alright.
Education requires this course?
What'd you say?
Education requires this course?
Yeah, they do.
But
Or
but
science.
those weren't
Has anyone ever taken this course that's been education major?
Yeah, in fact, Larry Lonnie used to teach over the summer all the time, specifically for education majors. I have a feeling it would be dumbed down there.
I have a feeling.
And that's not mean to education majors, I'm just saying I don't know that they would have had the physics to be able to do it right. Brad, on the other hand, is smart, and he's not lazy, he's very capable.
You in education?
Yeah, he's education. So, which is the reason he's taking physics by inquiry, which is ridiculous. At the same time, he's taking modern physics. So he's over there figuring out how to use a thermometer while simultaneously, using Schrodinger's equation.
It's all good.
Yeah, it is. All right, L is not equal to 0, A is not equal to 0. K also can't be equal to 0. Because if K is equal to 0, we still have the sign of 0. How do I make this, is there any possible way that I can make this equal to 0?
K L is equal to 2 pi.
There you go. There are more than one way to make, there's more than one way to make sign equal to 0. Sine of 0 degrees is equal to 0. What's the next time that sine is equal to 0?
180.
180 degrees. 180 degrees and 360, etc. These are all the places where sine is equal to 0, so we just need to use that. So this is pi in terms of radius, this is 2 pi. So we can simply make the requirement that KL is equal to n pi, where n is some integer, some positive integer, 1, 2, 3, etc. And n can't be equal to 0. 0 would be the case where we're on this corner over here. We're taking care of that. So n has to be a positive number, which will have implications later too. All right, that will allow us to get away with this. Ta-da! And it turns out that's all we have to do. All right, so now we've got a new version of this. I can say that my sine of x is equal to a sine, and instead of k, I can put n pi over L in here. Okay, so I'm going to have n pi x over L.
It's a weird looking.
N pi, not 2 pi.
Yeah.
One bonus point.
Well, let's see how broke I am by the end of this. Jared, what, you already got like $3 on anything? Wait, no, these got $1, you have 2, I think. All right, n pi x over L. Ta-da! Now, that will work out just handy for us, but there's something else we might want to know. We already had k as being something screwy that we had over here before. K is equal to 2m over h bar squared. That doesn't go away. We invented k. We need to keep that around. So if I go back over here and I look at this KL equals n pi, I now have to write this in as square root of 2me over h bar squared times L is equal to n pi. This has certain implications. So let's go ahead and just solve this thing for e. Did we do that now or did we do that later? Yeah, why not? We'll do it now. Square everything. So I'm going to end up with 2me over h bar squared, L squared, n squared, pi squared, and solve all this for e. E is equal to, we're going to have n squared, pi squared, h bar squared, divided by 2m L squared. Who erased this word? Okay. Important, extremely important. Now, the whole idea of this is we just started with this particle in a box and we said, okay, it's trapped here. Now, because of that, we solved this function here and it came up with this idea that, okay, the only solution for this is the sine function. And according to this, this said that energy has to be equal to n squared blah, 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 blah. Point being is that n are these integer values. N can't be 1.1. Which means energy has to be discrete values. This is where this whole quantization comes from. energy can only be certain values. Now this is entirely based on the premises that we believe this weirdo equation that we started this entire chapter from that just went poof out of nowhere. So where did this equation even come from in the first place? Because fine, you invented an equation that had this weird solution that said energy was quantized. That doesn't really make me believe anything. Where this comes back from is think about the laser that would look through the two slits. Some guy stared at that stupid pattern long enough to figure out I need an equation that defines why this laser goes through two slits, or even just one slit when it goes through one slit, and all of a sudden gets this pretty diffraction grating across the wall. It doesn't make any sense. Some of the light should go through, and I should just have a dot over there. And it turns out that there's this spreading across that. And that was the equation that he came up with that seemed to work. Schrodinger came up with Schrodinger's equation, it seemed to work. And then ever since then, we just keep testing it. We keep testing against more and more solutions, and it seems to work. There's no, let's come up with Schrodinger's equation, let's derive it from first principles, here's A plus B equals Schrodinger's equation. No, it was pulled out of hair. And it just works, as far as we can tell. So everything that we're doing from here is taking this weird thing that seems to work, this Rosetta Stone of physics, and applying all these random things to it. And one of the things it says is, by the way, energy can only be certain levels. It can be 1 and 4, it cannot be 2 or 3. Tough, sorry. And then all the implications that are associated with this. And they're all weird. They're all very weird. Alright, so let's see some of the more of the weirdness.
I'd like to see it weird.
Okay, what did you say?
I'd like to see it weird.
That it's going to be weird?
That's not going to be.
What part of this class has not been weird so far?
Well, that's funny. By this point, anything that's weird just isn't weird anymore.
So the thing is, we don't know what the normal is anymore to define this as weird.
Alright, fair enough. Okay, let's see.
And we do, it's just like, okay, yeah, makes sense. Particles can be through walls that don't exist.
Just take everything I say. Exactly, we're too close to December, damn it.
No, this is too.
I've kind of been like this the entire semester. Regular physics, I understood.
This, like, they would have quantum. I'm going to have the same feeling of, okay, I'll accept this.
Well,
just gonna have nightmares. No, dumb girls, no, don't teach me this.
To be honest, this is the reason I restructured the course the way it is. Last time, it was only 2 weeks of the intro of special relativity, and then it was all this stuff. I'd rather just treat this stuff as an intro stuff, and if you like it, take quantum, and maybe you'll understand it by the end of that, and spend our time on special relativity. I had hopes that you guys would really understand special relativity, that you'd now be like, I get that.
I just don't
I'm
get
just gonna
on
to
how
pretend.
Interstellar that the difference from 1 hour is 7 years.
No, I understand.
How did it know? I thought.
Well, because remember when we talked about the satellites?
Yeah.
I said that there was the time sync difference because here, because we're deeper in the gravitational field, that's the same thing.
Okay.
So the difference being there is we're Earth, which is a relatively small gravitational body. We have a small amount of mass.
Oh,
And then
it's
you
so
take-
close to the black hole.
Then you take a black hole that all of a sudden is a enormous, relatively infinite gravitational source, and then so your time is hopes. So you go inside a black hole, time doesn't really change, which in theory, and that's why you get the whole everything that happened there. So I mean, up to that point, and really, they could have said anything they wanted in there. I mean, it could have been, Charlie the Unicorn and rainbows everywhere inside there. We couldn't argue with it because we don't know. But up to that point, the physics was actually pretty sound, which was cool. Except the fact that they went into that blind. When they go down on the giant wave planet, he then explains, he goes, this might have just happened a couple minutes ago, she might have died. Where was the in-flight briefing about that on the way there?
Yeah.
If they knew that, then that should have been discussed.
So, we're talking about the movie.
Yo, you missed that? Oh, sorry.
You haven't seen
You
Interstellar?
were talking about
And you're
Interstellar.
taking modern physics and you've never seen
You
that?
really
Yeah.
should see that.
Like, that should be a prerequisite for this
It'll
class.
make me understand this class.
That'll be extra credit for the final while it goes through.
Be happy with that.
Okay, so back to this stuff.
I'm upset, I'm holding to it, you're on camera.
Okay.
Hold it.
2 mils. All right. This is for when n equals 1, and we have a new phrase for this. When n is equal to 1, we call this now the ground state. Okay. So when that happens, we have the ground state energy.
We're back to chemistry.
I remember this.
There you go. Ground state energy, the minimum amount of energy that you could possibly have. And this comes back to the Heisenberg uncertainty principle. You can't have small amount of energy. You're not allowed to have zero energy. I'm sorry. That is not allowed. So the idea becomes, when we talk about Heisenberg's uncertainty principle, it's like, all right, so how well do you know the position? Well, how big is the box? That is your undefinedness. Depending on how big your box is, that distance L, that is your delta x. Well, then I can tell you what your delta p is, your momentum. That combined with this says that, yes, you must have a certain amount of energy because you have a certain amount of momentum. Heisenberg says so. You can't just have no energy. It doesn't work. So,
what about an absolute zero?
yeah, so when we talk about absolute zero on a Kelvin scale, that's in theory when things are stopped. Well, it turns out according to this, that doesn't ever actually happen.
You get really close.
You can get as close as you want, you can't actually do it.
Take infinite energy.
It would take infinite energy to stop you. So then the idea becomes, okay, so let's say from an entropy standpoint, everything spreads out, all energy spreads out, right? Or everything even slows down to the point that it has the minimum amount of energy, according to Schrodinger and the Heisenberg uncertainty principle. How much energy is left? Well, the bigger question is how much energy is left just depends on how well you want to define where everything is. If you don't want to define where anything is, then you can say that there's virtually zero energy because you just don't know where anything is. If you say, I know where everything is really well, then all of a sudden there's a lot of energy in the universe. Then you have the choice of one or the other. Heisenberg says so. And Schrodinger is just there to back him up. Says, yep, that's true. Okay. All right, so now the weirdness continues. We have this solution, yay. We found a way for it to go to zero at the bottom. That's fine. Now what we want to do is we want to figure out a way to get this such that when we look for the particle, the answer is yes. We look for the particle, yes. Okay, so we found a total of 1. If we integrate all the probability across the entire probability density function, we should get back to 1. Which is not to say that we don't want to find David 70% chance that he's on the left side of the room and 70% chance he's on the right side of the room. Same thing we were talking before. Then that means there's a total of 1.4 chance of finding David. And we don't want to find 1.4 David. That's bad. That'd be very bad. And hopefully it would be divided into 1.4. Even though that's gross, anything else is even more gross. We got like 3/4 of a David.
Does that take a physics point 4 more?
Wait, what?
Does that make a physics point 4 more?
No.
You'd probably be dead.
All right, onward. All right, so to normalize this function, all that means is if we integrate underneath the curve, so whatever we find, and if we look at the possible solutions to this, which we will in a little while, we'll find that they're
You're not
not.
seeing any of that.
Really? Glare?
Glare from the window.
Okay. I'll remember. We're going to find that in the well, our wave functions are going to look like something like this, etc., and it's going to go on. So the idea is we want to integrate the area underneath here, and it needs to be equal to 1. The probability of finding this particle has to be 1. But we don't just integrate the probability function. What do we integrate? Yes, the intensity, which is the probability density. Just terminology, but you need to know it so that when you're reading a problem, you know what you're looking for. So this is the probability function. This is the probability density. Now, technically, we need to always do this as the entire wave function, psi star psi, which is this part and the temporal part, and blah, 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 blah. Now, the fact that you're only dealing with real numbers here, there are no imaginary numbers, and the temporal part goes out, it turns out that psi star psi is just equal to this for us. And this is only for right now. This will change later on. So we have to be careful. We can't always be this lazy, because later on the position part might not only be might only have real parts. It might actually have some imaginary parts. But right now we can get away with this. So now I can say that the integral over all space of my psi squared of x dx must equal 1. That is my goal. Okay. So, what is that going to be? Up here. Well, first of all, what is all space? Sure. What is the probability of finding it in the walls? 1. Oh,
0.
0. Finding, oh, you thought I meant in between the walls.
Yeah.
No. In the walls, it's not going to be there. So we could put this as negative to infinity, but we know it can't be outside the wall. So I could just write this as 0 to L. And this is the way we get rid of those stupid infinities. Oh, man. Sorry, guys. Allergies. Alright. So we gotta put in our function here. A times k of x, and we need to square this thing dx is equal to 1. Now remember that we had before that KL is equal to n pi, so we can go ahead and put that in there if we want, because k is just this made up thing that we have. The a squared is going to come out because it's not a function of x. So now I end up with sine squared of n pi x over L dx. Alright, anybody remember how to integrate sine squared of x?
Oh, it's the same thing, just negative alpha.
No.
You keep integrate by
That's
By
what-
our
you did keep
it gets to be a pain.
Doesn't it integrate like sine and cosine and both and all that?
No, here, let's go ahead, we're gonna, I'll write it down here. So the integral of sine squared of x dx is going to be equal to x over 2 times the sine of 2x, minus the sine of 2x. That's all it equals. Now, if in the event that I change this to be, well, here, I'll leave that there. And I'd say the integral of sine squared of ax. No, pick a new letter. We need a new letter. What do you got here? Ux. Hey, that's a good one. You often find that in the books anyways. X over 2 minus the sine of 2ux divided by, if I remember correctly, 4u. Yeah. So here's a couple trig identities, which I wanted to look up earlier, but Kyle had the book.
Just use Wolfman.
I tried. I don't like using that. I actually just went to an online integral table. I'm old school.
I'm gonna say, why don't you just use one in Aftermath? Is it like 600 list?
Yeah, that's what we use.
That's
Oh,
like
the
four.
hands out.
Yeah.
Yeah, I gave him a book that I really liked that I used all throughout grad school. It's very handy.
Let's say 4U or 4.
For you.
That's what's
That is actually, that was 44?
Yeah.
Cal, did you get my book?
Yes.
So yeah, I got a point or $1.
No, that was just sloppy handwriting.
Same thing.
It doesn't count.
It's like leaving off a unit still.
Hey, how good is that? There's like virtually no units ever in this class. That makes it a little bit easier.
That's
I don't know how you guys about that.
You still do.
I'm just saying,
Yeah, well, when you guys bring the one. Alright, a squared. 0 to L of this thing. Actually, I can just write down the result now. Alright, so I'm going to have x over 2. This is not even affected by that thing. So we still have x over 2 minus the sine of 2, whatever our u is. And it's this n pi over L. N pi x over L. All divided by 4 n pi over L. And this is evaluated at 0 and L. Alright, we're going to go through this one in detail, but the future one we will not. So let's plug L in first. Alright, so I end up with a squared times, still going to have this giant parentheses, L over 2 minus the sine of 2n pi L over L divided by 4n pi over L minus 0 over 2 plus sine of, well, it's going to be 2n pi times 0 over L. So who cares? Some junk underneath there. Let's look at these individual terms.
That would equal to 1.
Yeah, we haven't even got to that part, but yes, we're trying to set this equal to 1. I left that off just because I don't like dragging it around. This is 0. Go figure. This is sine of 0. That's 0. This is sine of 2n pi times 1, or sine of 2n pi. that's guaranteed always be 0. Okay, so it turns out that this whole wonky thing is just going to be equal to a squared L over 2, and then we come back to the whole point of all of this, was if we did this integral to make this thing equal to 1. Now, if I make you do this, the integrals will be simple, the functions will be simple, and I will give you the integral table, and it won't be 86 pages. How do you do that for the PQ test? You just give you all of them and say good luck?
He put the integrals that we had to use on the test.
Oh, I'm testing the test.
Yeah.
Okay. So, I can do that. That's easy. All right, so, what were we trying to do with this in the first place? Oh yeah, solve what A is. We need to know what A is. So I'm going to go back and put that into here. So A must equal the square root of 2 over L. I really don't know why I put it there. It's a very random place to put it. All right, erasing this. We get over here?
See.
You know, I had the bright idea to take, I wanted to go to Germany. I was going to study German for a while, and physics and German.
That sounds stupid.
It's a terrible idea. And my advisor in undergrad goes, you realize that people that go overseas to study, they're studying more German. They're usually German majors. They're trying to study, a subject that you don't know in a language you barely know. Probably not a good idea. I don't know what the hell I was thinking. Very glad you talked me out of it, though. Not to mention, I'm terrible at foreign language. I've always been terrible at foreign language.
The other people who go to Germany from here are people who aren't real majors.
What was it from here? It was from my school. But, my school, you had to do a term overseas at a different school someplace around the world. That was part of the requirement to graduate. So that's why I ended up going to New Zealand. What?
I do that.
Yeah.
Oh, man.
And I just forgot to come back for a while.
Man,
I know, it was so terrible. So, I was there for 8 months, something like that. Good times. Long enough that, I was supposed to come back, because their term starts in June, something like that, and it ends before Thanksgiving. Kind of missed a couple holidays there. I just didn't want to come home. I came home the day before Christmas so that my mom would kill me. So, alright. I came home kicking and screaming when And so, we now have a more complete wave function. X is equal to square root of 2 over L times the sine of n. I wrote 2 again. N pi x over L.
Try to
I don't know what that's wrong with me. So we now have 2 equations that we came out of this. This one and this one. Now keep in mind this is only a solution for the most ridiculous case. And we have these infinite potential walls, blah, blah, blah. But this is the solution. So what do we do with that now? Well, we can look at what it's going to look like for different n values. Let's look at for, say, n1, and n2, n3, n4. And this is where we're going to use your book. So if you guys have a book, or sit next to somebody who does,
Another day I did bring it.
So one
I don't use a book.
One day I didn't bring it.
Yeah, so one.
Okay.
Thanks for the book.
Genders.
Yeah.
Okay.
Got it.
Page 153.
I'll give my card.
So we talked about the different wave functions, and they're on the top right page. Page 153. So here we've got what the ground state is, and then the second energy level, third energy level, and the fourth energy level.
Okay, I've seen this before.
Yeah, alright.
Wait, so are the nodes where it equals 0?
The nodes are where it equals 0. Yes, any nodes are where it's the maximum and minimum.
Which makes no sense.
It's always bothered me too, but such is life. Now the top one is the probability function. The bottom one is size squared, so therefore it's the probability density. Which makes everything positive, which is good, because we don't want to find there's a negative % chance of finding something somewhere. I don't even know what that means.
You ain't gonna find it.
Yeah, you're really not going to find it. Don't even bother looking.
It's called just a particle, so it can never once.
Wait, what? You lost me there.
It's a particle. It's a particle. You can do it every once.
Alright, back to this guy. So the full equation for this, if I get rid of the ground state, I have to put my n squared back in here. So, now let's talk about the different energies that are associated with this. For n equals 1, which we have over here. For n equals 1, we've got some sort of energy 1, which we can now calculate. Look what it requires to calculate this. This is the other thing that's really interesting. Pi, okay, fine. N, we have to know what that is. H bar squared, that's a constant. Mass, presumably we know what we're dealing with, an electron or something like that. The energy associated with the particle is simply a function of the dimensions that you trap it in. It's just geometry. It's just really weird, and I have no way to really probably make you feel better about that.
Sounds like simple
I
geometry.
accept it.
Wait,
Rar.
wait, okay. So the energy of the thing is dependent on the box you put it in.
Yes.
So
That's all that matters.
Wait.
And the way to make yourself feel better, I wasn't sure if you're making fun of me at first.
No,
I know, I wasn't
But
sure.
that's like, I don't know, that seems really
Very
counterintuitive.
strange. And the idea, it just think back to Heisenberg's uncertainty principle. What it comes down to is the fact that if L is very, very small, then it can't have that defining position. Or if it does have that defining position, because it is in the front box, then it has to have a huge amount of momentum. Because this whole idea of saying that the infinite potential walls are zero, we're really kicking, Heisenberg in the nuts on this one. Because we're saying, okay, my position is uncertain. No, it is not. It is not. I have infinite walls of potential. Screw you. You are in the middle, whether you want to be or not. So if we force that to be that precise and say that there's no possible way it could be anywhere else, then the energy has to be a certain level, and it's based on that width. Here we go.
Okay, see, I think I'm really understanding. See, to me, the energy thing makes sense because the larger the box means the more the box can bounce around, right?
Yeah, but what's your point? The energy will be smaller.
Yeah, energy will still be the same no matter how far.
Also, keep in mind this is in the denominator. So the second this becomes a relatively large quantity, and by relatively large, we're going to see here in a second, 1 millimeter is huge. This energy level is virtually zero. It's way too low to be detected, and as far as we're concerned, it is zero energy. So the minimal amount of energy in a relatively large box, being a micrometer, is zero for as many digits as our calculator can handle. This is only of use when we're down to the nanometer size boxes and things like that, where we're really pinning things down to very, very small amounts. So again, also, the other way to think about it is, this only becomes a problem when you're trying to pin something down on the range of its wavelength in the first place. We say that things have nanometer wavelengths, okay? So if you're trying to put it in a box smaller than that, okay, fine. Then that's when you get into problems. So, all right, but when I want to talk about the energy, not only is it quantized, but it's kind of interesting in the sense that N1 is equal to E1, N2 is going to be equal to, well, N2 squared, so it's going to be 4E1. N3 is going to be equal to 9E1. And so forth, it goes up. So not only is it quantized, but you'll see in the scale that they're showing them that each energy level is higher. Now, what I don't like about these diagrams, and they don't bother to explain, is the height on them. All they're doing now is they're representing the vertical scale as a certain amount of energy. So they're doing the same thing that we did before when we talked about, when we had the well and we said that, okay, when it comes out of here, it had to climb a potential well, so it had more energy. And we called this distance here the total energy that it had. It's just a diagram. It doesn't mean that the particle's actually higher in the well or lower in the well or anything. It's just a way to represent multiple graphs on the same diagram. To say that if a particle does have higher energy, it's going to have a smaller wavelength, and it is going to have more nodes and antinodes. All right, next. This part of, I'm all over the place. I'm going to erase to come back over here. Another story, but I don't have time. I'll tell you stories. I gotta go.
No, it's your story.
No story.
Doesn't matter.
So you've got this one thing, and you've got this dashed line in here. What does the dashed line have to do with anything? The dashed line is the temporal part of this wave function that we're not looking at right now. Okay, that actually changes with time. You can think of this as just like the standing waves. If you guys, did you have standing wave generators? Did Simmons use those in class? Where they actually create the standing waves?
I had stuff.
No, he did. Did he use them?
I don't remember.
Sure, I was looking, he came up earlier today because we need to get the telescope set back. He might heard what happened.
Wait,
I
what?
tried to do some internet searches. I couldn't find out what happened. There's no more information that I can find online. But anyway, Yes, Jen stopped.
Oh, okay.
It disappeared?
Not very quiet whisper.
So wait, he was here?
No,
Oh.
we're just trying to get, Hamilton's trying to get equipment back. He's got a lot of telescopes and stuff.
Hmm.
Anyway, so this temporal part here, it's just like the actual same wave. So if you create a jump rope, or just go with the same waves, where we had the string, where it was vibrating up and down, and it looked like it had a wave like this, and looked like it had a wave like this, because it was going back and forth. And the temporal part of the wave function is what defines that. Point being is this is not real, and this is part of the, well, it isn't real, it's an imaginary part of the equation. But it has no purpose, it has no meaning whatsoever, so don't even think about that. The only thing you need to think about is the bottom one, the one on the bottom right, where we have the probability density. That's real. That's saying that the particle will exist in certain places. Psi squared is the probability density. Hopefully we know that pretty well by now. What was I doing that I drew this up here? Do you guys see that still?
Here's some like 3 weeks ago.
Alright, next. Another way to the energy. Energy. Okay, energy we stated was n squared, pi squared, h bar squared, over 2ml squared. And we came with this out of some artifact of manipulating the Schrodinger equation and constants and whatnot. Turns out that there's a lot easier way to get there. So, maybe this will make you believe a little bit more. Now, for standing waves, our wavelength has to be equal to this. What the heck am I talking about? Alright, so if I have a standing wave, the lowest standing wave I can have, the largest wavelength is this. Okay, now if this is a length L, what is my wavelength of this function?
1.
No.
L over 2.
Vice versa, 2L. And the reason being is that the wave function, this is one wavelength from here all the way out to here. That's one wavelength. So the largest standing wave you can have actually has a wavelength equal to 2L. Does that make sense? Do you remember that? And then everyone short of that, the next smallest you can have is this one that looks like this. And then that's going to have a wavelength exactly equal to L, and then everyone after that's going to be smaller. So the reason I'm bringing this up is because apparently we just solved this, and I'm saying the probability density functions are equal to these standing waves. All right, fine. If that's the case, then I can say that the wavelength of the particle is this standing wave. So we talk about the probability density, the likelihood of finding the particle here, it's synonymous with saying that is the particle's wavelength. Okay? That's why we can treat the particle like a wave, because we're saying it's not in one position. It's in all of these positions to some degree. Does that make sense? We talk about the wave-particle duality. We say that a particle sometimes behaves as a particle, sometimes it behaves like a wave. This is now the application of it. When we say it's acting like a wave, we're saying because it won't be found in one place. It's going to be found in one of these wavy-looking patterns. That's what it means to act like a wave. Okay. So here's the wavelength we have for that. Next, we can note that we already know we've got this HK business, where P is equal to HK. But K has a very defined purpose here. K is the wave number, and we just say that is just 2 pi over the wavelength. It's easier to write this as K. So the K that we were working with earlier today was just pick a random letter and throw that in there, and we were just using that to run around to make the math easier. This K is the wave number, which has a very specific purpose, 2 pi over the wavelength. So, now what am I going to do? Well, I can note that the energy of a particle, again, we're not talking about its rest energy. We care less about that. We only care about its kinetic energy. Its kinetic energy is equal to 1/2 mv squared. 1/2 mv squared, which I can also write as p squared over 2m, which now becomes h bar squared k squared over 2m. All right, well, what is k squared? K squared is 2 pi over lambda. All right, fine. So I get h bar squared, 2 squared, so I have 4 pi squared over 2m lambda squared. What the hell is lambda? 2L over n. All right, fine. H bar squared 4 pi squared 2m times what's going to be 4 squared L squared over n squared. 4 squared? No, 2 squared, which is 4. That goes away. I end up with n squared pi squared h bar squared over 2ml. the same equation we just had a second ago. Now, I probably could have done that in less steps, but you get the idea. So, this is using the wave-particle duality for the function of momentum, saying that the particle only has kinetic energy. And because of that, we know that the particle's wave is a function of the box size. We get back to the same energy equation.
What did the square on the L do?
3 points for Jerry.
It's 4 now.
Is that 4 now?
Oh, I got one.
You did not.
I did too. You know
You
what?
couldn't read my writing. It
Okay,
doesn't
so
count.
when everyone else thinks it's 44,
Okay, this is look at this. If I wrote that and he caught it, would you count it as him correcting something?
Well, if we all want to get rich, we'll just let you write anything on the board.
shots fired.
I'm up for this.
Okay. Okay, that's the energy, just shown in a different way. So let's believe this equation because it's real and stuff. That's a good idea.
No, shots fired because it's so quick.
Okay, next. Alright, the ground state, where n equals 1, where E is the ground state energy. This is generally where the things are the weirdest. This is where the things act the most quantum. When we start getting up to high n values, they're not so weird. What is the cartoon? You're going to have to put a camera over him.
Alright, camera right there.
Example 5.1.
Turns the NSA over.
Let's solve a problem with this stuff now.
No.
Example 5.1, and you might move it back here. What's
Sadly, this isn't that bad.
Did you say sadly?
I'm saying this looks bad, but at this point, it isn't that bad.
an electron confined to an infinite well, the ground state energy of 0.1 eV. A, what is the well length? Let's start simple. So, we are in one of these infinite wells. Infinity. So, if I say that the electron, E1, the ground state is equal to 0.1 eV, then the question is, what is my L? That's all it wants to know. Now, first of all, energy. What is the SI unit for energy? Joules, not electron volts. How do we go from electron volts to joules?
1.6 times 10 to the negative 19.
Yes, then what do we do with it? Divide or multiply?
It's that many joules.
No.
So
We'll vote. Who votes multiply? I think there was going to raise your hand for divide. Who divide?
Maybe.
Multiply.
3. So wait. Do you guys have a vote?
Multiply.
it's multiply because it's
It's multiply.
Yeah, I'm right.
I knew that.
So if we multiply by 1.6 times 10 to the negative 19 joules, and if you want, you can think of it as joules per EV. So if you just put the units on that, it's joules per EV, then you're always going to get it right. And we're going to get the answer. Now, this just obviously becomes 1.6 times 10 to the minus 20. Don't bother to take out your calculators. That is our energy. Now we can say that that value, E, is equal to our n squared, h bar squared, pi squared, over 2ml squared. Solve for L. L is the thing that we're interested in. All right, L is going to be equal to n h pi over the square root of 2me. What you say?
n is 1.
N is 1. Yeah. So I can, n is 1. Now we got $1. H bar here, well, we can throw it in a second. I have pi over 2me. Now,
It should be squared.
huh? No. L was squared, so take the square root.
Okay.
I win. Alright, n is equal to 1. Now, I don't like h bars, because I never remember what it is. I always remember that h bar is equal to h over 2 pi, though. That's handy to me, because I can now rewrite this as h over 2 divided by the square root of 2 times 911 times 10 to the minus 31 kilograms times what we have here, 1.6 times 10 to the minus 20 joules. And I can get numbers associated with this. H being, of course, 6.63 times 10 to the minus 34 joule seconds. What have I done before? Did I just put those on the sheets?
What?
H
Sure.
bar and H. Or did I make you guys memorize those?
It's on the sheets.
Why did you guys memorize it in the last test?
No, don't think so.
I've known it for a while, so I don't remember.
Yeah,
I think you might have made us memorize, but I don't remember.
I think you said
We
machine.
have H bar. I don't think it was used.
Not H bar, H.
Yeah, you
H bar is like 1.055, I think. I don't like it, so I never memorize
it all.
Yeah.
We'll see when I have you memorize. We'll see how extent it gets. But things like electron mass, I do need you to know that. That's stuff I want you to come out of here with. Planck's constant would be nice, but you don't really need that anytime. Alright, anyways, let's push buttons. We get a length of what? 1.94 millimeters. I'll skip ahead on it. Put that in the calculator, you get 1.94 millimeters. Trust me, it happens. So this is only a problem when we get to the really, really small lengths. Alright, part B. I'll erase all this. Everyone got this written down?
That wasn't it?
No, what's the problem?
That was part A of it. A through D.
We have 15 minutes to get through this.
And I don't even think we're going to get all the way through D.
Are you serious?
I'm okay with this.
Okay, B says, what is the probability that the electron will be found in the first left-hand third of the well? Alright, so we've got this well right here, and I want to know what is the probability of finding it in this section right here.
Why can't it be as simple as 1/3?
No, wouldn't that be great?
That'd be
1/3
great.
would be logical. It's
Yeah.
not.
So, you
So,
know,
how do we find that?
if you do about half,
Well,
Integrals and crap.
From 0 to 1
half the box or 3.
So all we have to do is integrate our probability density function from 0 to 3. Now remember, it doesn't make any sense to say, what is the probability of the particle here? And we always have to ask, what is the probability of the particle being in some sort of range? In this case, we're going to deal with the first third, 0 over L3. And we've got our a squared, which is going to come out here. And then inside here, we've got the sine of n pi x over L squared dx. All right, this gets just as ugly as it did last time. It's not a whole lot easier. So we end up with an equation I've got written here. A squared is going to be 2 over L times x over 2 minus L times the sine of 2 pi x over L, all divided by 4 pi. Should I really know why did they do that? Why did they do that? It's so confusing written that way. I'm going to write it this way, where I put the L underneath there. It's the same thing, but it's easier for me to understand what else going on. Evaluated on 0 to L3. Now, 0 is not interesting because everything goes to 0. Now, when we have L over 3, though, this thing doesn't go to 0 anymore, so we have to keep that around. So, this is going to be equal to, all right, we still have this 2 over L, which we'll have to deal with here in a minute. And then now I've got L over 6 right here, minus, this is going to become sine of, well, 2 pi 3. 2 pi over 3.
Where's this come from? Oh, whatever.
All divided by 4 pi.
So why is that not multiplied by on the last
Alright, so multiply all this through. I'll jump down here so we go to the so I end up with 1/3 minus, well, I've got the 2 pi L here, so the L is going to cancel. So I'm going to end up over 2 pi, so I'm going to end up with sine of 2 pi over 3 over 2 pi. So 1/3 minus quantumness. It would be lovely if it was 1/3, but the answer is not 1/3. It's going to be something less than this by this factor. Okay, so that factor ends up being equal to, I get 1/3, and this numerator's 0.866, and the denominator's whatever 2 pi is. I'll just throw that in my calculator.
Do we assume n is 1?
1955. Wait, what?
Do we assume n is 1 unless told otherwise?
Yeah, ground state. It specifically told us the energy of the ground state, so we're working in the ground state. No, it has to tell you what we're dealing with. In this case, it says ground state. Because in your homework, you'll talk about like the first energized state, which means the first state over
So
the ground state, so 2. And the second energized state is N3. So you got to be careful on that. That's the wording on that. All right, so 0.195, which is less than 1/3. Now, if we go look at a diagram of this, this is what it's going to look like. So instead of, if it was going to be this function like this, then if we were interested in the part underneath here, then yes, of course it would be 1/3. But instead, we only have this part right here. Now, for the people that love math, what you can go back and do is you can prove to yourself that this region right here, mathematically, is this quantity right here. Okay? It has to be. Come on, for a good time, go prove this is true.
Bonus points over there.
Yeah. What's wrong with that?
I'd rather take diagnostics again. No, actually, that's a lie. Screw that.
So we got that. That was part B. On to part C.
Let's hear a story.
Part C says what would be the next higher allowed energy? Alright, next higher allowed energy, E2, the first energized energy state. Alright, let's go figure that out. Well, we now have a length and everything, so I can say that E is going to be equal to still n squared h bar squared times pi squared over 2m L squared. Now I have a lot of that information. For example, n squared is going to be 4 times, and look, I can make this be h over 4, we just let in mind. How did I do that again?
H over 4 times pi.
Yeah, I'm going to do 6. We'll get through 6 pages.
Send me a record.
Yeah, but how does that go away for some reason? Oh, I know why. Because I have this 4 over here. So I've got 4 times h bar, this right quantity right here, when this is equal to 2, just makes this nice and easy. And it just goes h squared, because it would be h over 4 times pi squared, or h over 2 squared times pi squared. It goes away. So nice. And then I've got 2 times 9.11 times 10 to the minus 31 kilograms times our length, which we said is 1.94 times 10 to the minus 9 meters. Is small. Is small box. So we push the buttons. And we push the buttons, and we get an energy that is equal to what I've got here is 6.4 times 10 to the minus 20 joules. Now, if I want to figure out what that is in EV, now I divide. If I divide, and put subscripts on this, I'm being sloppy. E2 means this is the first energized state. This equals 0.4 EV. Now, as it turns out, this is the very long and obnoxious way to do this. We could have done it a whole lot easier. Remember we started this off a little while ago saying that, well, E2 is equal to N2 squared times E1. E3 is necessarily going to be equal to N3 squared times E3, which is the same thing as saying not 1. Do I get to pay myself? No, I need to say
Save yourself.
41, 91. So I could have just said 4 times the original energy here, which is 0.1 EV, and save myself a headache.
Helpful.
Helpful. Yes, but I wanted you guys to know that you can do it that way. There's more than one way to skin this cat. Schrodinger's cat.
So, we're
Okay,
not dead?
Wait, what?
Why would you skin a live cat that might be dead?
Yeah.
That might be dead.
Yeah,
My
it's
skin
both
is
alive
because
and
it might
it's
be
Schrodinger's cat.
It's both
You
alive
skin
and dead.
Schrodinger's cat. Was it alive or dead? All right, D. What about if L is increased to an increment of 1 millimeter? N equal to 1 millimeter. What happens? L.
Physics happens.
I think I beat you on that one. $1 for you. All right. L is equal to 1 millimeters. No. B. Okay.
So they want to change the energy?
Well, no, but it gives us the same energy. So we've got an L of this, and we've got an energy of question mark equal to 0.1 EV. So we still got this low energy level, but we don't know what this is of. So the idea is to solve for N. What is N going to be? So we just take that equation and we find stuff. So we're going to say that N is equal to 2m L squared E divided by h bar squared pi squared. And take the square root of all of this junk. Put a lot of stuff in there. So if we get the same energy, and we have to put all the stuff in there, you can do the same trick with the h value. I can say that this is going to be equal to, alright, let's simplify this, 2me, and you often get this quantity right here, 2me, times our L, divided by h over 2. So I can use Planck's constant instead of h bar. Or, yeah. Use myself there for a second. So you use Planck's constant over 2, and I get an answer of 515,051. That is what my n value is. But you might have noticed that n is also the same number of antinodes. So for the ground state, when n is equal to 1, we get the 1 nice bubble. What this means is the probability function for this is going to look like this. 515,000 nodes and antinodes. Now, if you integrated all these, you would still get 1 back. Oh, great. So there's a tiny little surface underneath here like this. It's basically a straight line. So the point being is that 500,000 of these in the size of a millimeter. So this is why we say that position isn't quantized on a large scale. Okay, yes, in 1 millimeter space, technically an electron can't be in all locations, but it can be in 500,000 locations in that one space. So we get to the macroscopic point of view where we can't tell that there's a difference. From our point of view, that looks like it's continuous. 500,000 is often again continuous on a 1 millimeter scale. Okay, and this is for any equaling this.
So
The second part is it wants to know what the energy level associated with this is.
this part 2, part 3.
Now, this is D. Now you'll find that the energy level associated with this is practically 0. The energy can be a whole lot lower. Why? Because we're trapped in a much larger box. If the box gets larger, our wavelength is allowed to be larger, which is to say that we can have energy that's virtually 0.
So there's what E1 was?
Yeah, so E1 in this case is going to be so incredibly small, it works out to be
So you take the 1.6 times 10 to the negative
yeah, they're
20
showing what
divided
the
by.
changes. I don't know why they don't actually have the answer here.
Is it the 4 times 10 to the negative 6? That's a fractional change.
That's the fractional change. That's why I don't know why they didn't assume what the actual low energy is. The energy is going to be painfully low. I'm actually surprised we got through this, so I didn't finish the end of the problem. I thought we were going to be rushing. Not that we were going slow.
Story time.
No. I don't even remember what stories I was going to tell you. So, okay, point being is that the macroscopic scale, the energy can be 0. We can say that the book can sit here on the table and have 0 energy as far as we're concerned, because it's on such a large scale that its position is trapped in a very large box, so it doesn't need a very large momentum. Does that make sense? Okay, your homework.
Is to read.
It is. It's to finish this section. There's one more example problem that goes over this in a little bit more detail. So finish section 5.5.
That's all we're going to do is read?
No. Second to last. You will have one, and I haven't figured out how I want to handle that or how you guys want me to handle that.
It's chill coffee for me. So